Hey everybody, welcome back. Glad you're still here. The next set of enol and enolate reactions that we are going to talk about is halogenation. Now, frankly, this is the weirdest one of them, which is why I led off with alkylation, whereas your book kind of buries that partway through the chapter. I think alkylation makes a lot more sense. Now, when we talk about halogenation of enols and enolates, we're really talking about bromine. Ladies and gentlemen, chlorine isn't quite reactive enough. Iodine is just too weird. So we're going to be talking about the bromination of our enols and enolates. You will get different products if you go with the acid pathway versus the base pathway. And then, if you keep going on the base pathway and you have a very specific structural feature, then you're going to get an even further reaction. But before we do that, let's take a look at how the bromination would work. I want you to think back to the bromination of alkenes. You'll remember that the carbon-carbon double bond can induce a dipole. The carbon-carbon double bond can induce a dipole across the nonpolar benzene. So the high electron density of the alkene can scare the electrons that are around the bromine. You can hear them go eep and run the other way, and you wind up with a partial positive charge on the bromine and a partial negative charge on the further bromine. Now, left to their own devices, this will settle back out very quickly, and it will be as if nothing happened. However, if you still have that electron source, i.e. the alkene in our case, then a reaction can occur. And something very similar happens in the reaction of enols and enolates with the halogen. So let's start with this. Cyclohexanone, and we're going to react this with acid and bromine. All right, the product you will get here, and there's going to be a couple more products once we get done, but I want to discuss just at least the initial adduct mechanism. There's our product when you get done. So what I want you to do now is hit pause and then see if you can work through this mechanism. Here's the hint I will give you, all right? Here's the hint I'll give you. Acid. You know you've got acid from the H3O+. Think enol. Think enol as your mechanism. So go ahead, work this out. I will be right back. Okay, everybody, I'm glad you're back, and hopefully you had a good time working on this. So let's take a look at the mechanism here. As I said earlier, whoops, I don't want blue, I want white. As I said earlier, because this is an acidic pathway, you know that you're going to be dealing with an enol. So let's go ahead and start that dance. Pair of electrons on the ketone, grab the proton off the enol. Proton transfers on and off of oxygen are, that's right, fast and reversible. So now we are here. Our next step is to deprotonate one of the alpha carbons. And so now we have our enol. Now, for those of you who play along at home, you'll remember that the enol is very short-lived because it will tautomerize and go back to the ketone, and you would be right. But for the very small amount that lives and exists long enough for us to do something with, this is what will happen. You'll form the enol, reform the carbon-oxygen pi bond, attack the bromine, cleave the bromine, just like the bromination of an alkene that you saw earlier. There is no bromonium ion this time, though. What we have instead is this. Our brominated product. Now, I kind of drew myself into a corner here because we got to find some way of getting that hydrogen off. I just don't have room mechanistically for it, but I think I've done this enough that you can imagine all sorts of things that can pull the hydrogen off, and that leaves us with your product here. Now, here is the thing about the acid or enol mediated step for the bromination of ketones. We stop here. This is where we stop. So for the acid pathway, monobromination rules. For the acid pathway, you stop at monobromination. Now, before I get into the base, let me present you with this question. Let's say we have 2-butanone or methylethyl ketone. You react that with acid and your halogen. Take a minute and predict what you think the product would be. I'll be here. Oh, hey, you're back. All right, the product would look like this. That would be your product. And the reason being is when it comes down to making the enols in question, this enol is more stable than this enol. And that's all there is to it. The more substituted alkene wins. Now, when we switch over to the base or enolate mediated process, it gets a little weirder. So what I'm going to do for our examples here is I'm going to start using acetophenone. For reasons that are going to become apparent in just a minute. Well, okay, just a minute being right now. The reason I am using acetophenone here is you'll notice that we have 3 alpha protons on that side of the molecule. Yay, we do. On this side of the carbonyl, we have, whoops, sorry folks. On this side of the carbonyl, we have 0 alpha protons. So there's only one side that we can really work this. And in fact, I'm going to change this structure just because I like to be difficult, but no, because it's actually pretty important. I'm going to put an ethyl group there. So this is no longer acetophenone. You're wondering, why in the hell did he say all of this in the first place? You'll understand in just a few seconds, I promise. So there are 2 alpha protons there. So let's take a look at the mechanism and how this shakes down. We start here. And what we're going to do is, I'm sorry, I'm all messed up here. Let's do this instead. We're going to react that ketone with, let's just say excess. I want to use excess sodium hydroxide. No, it's not necessarily the best, but you'll see why here in a minute. excess sodium hydroxide and excess Br2. The product you get out of this is the geminal dibromide. So now, let's see how. Remember, we are using the base-mediated pathway here. So, first step is we deprotonate the ketone, that alpha carbon. We form the enolate. And we're here. Now, the bromination, reform the carbon-oxygen pi bond, attack the bromine, cleave off the other side, and we're here. Now, this is where, if we were in the acid pathway, we'd be done. The problem is we're not. There's still a proton on that alpha carbon. And that alpha carbon proton is going to get plucked off again. We're going to go through another enolate process and a second enolate, and therefore a second nucleophilic attack. And what we wind up with is, it's called perbromination. What that means is every site that can be brominated is. Every site that can be brominated is brominated. Okay, I'm going to call it quits for this video. There's one more thing with base-mediated bromination of a ketone, but I'm running out of time, and I don't want to go over my 15. So tune in next time to see what happens when you've got a methyl ketone that you're doing a base-driven bromination through enolate chemistry. I know you can hardly wait.